Okay, good evening everybody. Okay, today is the first time I'm doing my recording at home. Okay, today tutorial will be on conservation of energy. We will look at one classic example of how conservation of energy is being used, and we will look at the mathematics involved behind it. Okay, the question that you see here with his worksheet 7.1 is one of the questions that my student have. Okay, deal with an object, okay, 2 kg being dropped from rest, okay, from a building that is 7 meter high. Okay, from the questions you can see that there are a few important key things that we take note. One is the mass. Okay, so this will be the mass. Mass in physics, must remember, it usually must be in SI unit in kg. So students, you need to take note whether the mass, the unit given, is it in kg. The second key things that you look at from the question is the word rest. Rest, usually it has one implication. It tells us that the velocity at these instances, okay, is 0. Okay, to be exact, let's say we use the correct symbol. Okay, the initial velocity here will be 0 meter per second. Okay, so if required, we look at chapter 2 kinematics, you will need to draw a speed time graph. So which means this particular object, it actually starts from the origin, time 0, velocity is 0. The third one that we're looking at will be the height is 70 meter. Okay, same thing, height, okay, involved. This setting here, we will need to take note that the height is measured in SI unit, okay, because most of the formula that we deal with in physics usually needs to be in SI unit. Based on the question is that, what is the increase in kinetic energy when the object, before the object hits the ground? Okay, so let's say if I have a 70 meter high, okay, so let's say this is the height. I drop the ball all the way down to the bottom here. So before I hit the ground, okay, this will be the location. So which means that for the basic things that we are looking out for is as the ball drops, before it hit the ground, okay, the energy I'm looking at this instance here, the only energy that I'm looking out here will be actually EK, which is your kinetic energy. So what's the energy I have at the beginning? Beginning, remember, when I've dropped, okay, velocity is 0, which means that the object is just on top hovering, which is around 70 meters. So the energy I'm looking out for is actually only potential, gravitational potential energy. So at original location, the energy that I'm looking at is gravitational potential energy. And finally, I have kinetic energy. So the energy I'm looking at, the conservation energy I'm looking at, is actually from EP changes to EK, kinetic energy. Okay, so whatever kinetic energy I have at the end, actually comes from where? It comes from the potential energy at the beginning, which is why the mathematics behind it, you take a look at the concept I'm looking for is conservation of energy. The energy at final, which is number 2, will be equal to the energy at the initial, which is number 1. Okay, so potential energy, same thing, simple formula mgh. Okay, after that, make sure everything is in SI unit, plug it in, you should get your answer straight away, okay, using the calculator. Same thing, answers, just remember it has to be 2 or 3 SF, whichever is convenient for you. Okay, nothing more, nothing less. Now, what happened is, at the part 2 is, no energy is lost. Okay, so this is ideal stage. Okay, no energy is lost. Calculate the velocity of the object just before it hits the ground. So I want to take a look at what is the energy at these instances here. So if you look at velocity, in your syllabus, if you look at drop from rest 70 meter high, there are 2 possible ways of solving it. Okay, one will be looking at kinematics. Okay, one will be looking at energy. So we have one method of looking at energy, the other way is looking at kinematics. Okay, you can use kinematics to solve, no problem. Okay, but if you use kinematics, what are you looking at? You're looking at speed time graph. Okay, so you need to draw the speed time graph for this particular object. Okay, in the meantime, we'll look at the first one since we are at chapter 7, energy. Okay, we'll look at the method of using it to use, we use energy to solve. So after that, if you got time, you'll look at the second method, kinematics. We use kinematics to solve. Okay, you'll find that though we are using 2 different concepts, but we will still arrive at the same answer. Okay, so this is the second method. Okay, the first method that we're looking at for, if you use energy, you already have the kinetic energy, so you need to find speed. That's the easiest way is to just use the formula. Okay, kinetic energy is half mv squared. Okay, and you found that the energy given is 1004. So all you need to do is just substitute the formula, and after that, solve for velocity using your simple algebra. Okay, so you'll find that it will be 37.4 meter per second squared. 7.4 meter per second. Okay, now that we have solved using the energy approach, let's solve this question using the kinematics approach. If you look at it as a kinematic question, one of the important things that you need to take note for is this particular information. Okay, the question says that the block fall freely. Okay, the idea behind the marker giving us this particular word is to inform the student that the object falling freely means it's under the influence of gravity, which means the acceleration due to free fall is actually a fixed number, which is 10 meter per second squared. This information, coupled with the initial velocity, coupled with the initial velocity and the distance, it actually allows us to draw the velocity time graph. Okay, so if initial speed is 0 at time 0, okay, if you look at it in terms of VT graph, and acceleration is constant at 10 meter per second square, which will tell us that the velocity time graph is actually a straight line and it's actually increasing with time. Okay, and it starts from the origin. Okay, and you'll find that the velocity time graph that it arrives will be a upward sloping graph, and the area under the graph, which is the distance, is actually 70 meter. Okay, so which means that at certain time t, when I hit the ground, the distance traveled by the ball or by the object is actually a triangle, which is controlled by 70 meter. So which means that from this information, it actually tells us a few things. The area under the graph, which is a triangle, is actually 70 meter. So that would be the first clue or first equation that we have, which is half. Let's assume the final speed here is v. So it will be area under the graph, which is triangle, half base times height. The base is t. Okay, the height is v, and this will actually give us 70 meter. Okay, I need to erase some information to make space for this new working. So this picture have to go. So sorry about it. Okay, now the second information that the question has, okay, is the acceleration. Okay, remember for speed time graph, if you talk about acceleration, okay, it actually tells us one thing, which is the gradient of the graph. And gradient in math is actually rise over run. Okay, and this information will tell us that the rise, which is acceleration, which is 10, okay, meter per second square, and gradient formula for acceleration is actually rise over run in terms of math. So it will be final. Okay, the rise will be here, the run will be here. So you get v minus 0 divided by time taken. Okay, if you look at it from a mathematical point of view, this is what we call your rise over run. From physics point of view, it's actually the formula for acceleration, which is change in velocity over change in time. Okay, v minus u divided by delta t. So this will give us 10. If you manipulate the formula, you'll find that you have a second equation, okay, which is v equal to 10t. Now, for kinematics, like I mentioned before, when you have two equations, the next logical step that you're looking at is actually simultaneous equation. So with two equations, okay, the next thing you need is to substitute one into the other. But remember, the idea here is to solve for the unknown that the question wants. So now you have two variables, v and t. Okay, in terms of math, you need to solve for both. But in terms of physics, in this question, you actually only need to solve for one, which is you need to solve for the velocity of the object itself. Okay, so now let's solve for the velocity of the object. Okay, so let's solve for v directly. So let's solve. Okay, so from equation 2, okay, let's manipulate the thing. From v equal to 10t, I will make t the subject, v divided by 10. Okay, so this will be my equation 3. So what do I do now is I will substitute t equal to v over 10 into the first equation. Okay, remember the objective is to solve for velocity. So this is my equation 1. Okay, I will substitute equation 3 into equation 1. So I replace the t with v over 10. Okay, okay, and you'll find that you arrive at a simple equation of v squared, okay, equal to over 2 times v squared over 10 over 20 equal to 70. Same as algebra, okay, v squared over 20 equals 70. Now you solve for v directly. Okay, if you manipulate your math, you'll find that your v will end up with the same answer, which is 37.4 meter per second. Okay, both methods, if you look at it, both methods arrive at the same answer. Both methods are actually correct. But if you look at the mathematical manipulations, if you solve it using the kinematics equation, you'll find that the math involved is actually, I would say, at least 2.5 times more than the energy approach. Okay, because if you look at it as from the energy approach, it's just a simple half v squared. After that, equal to 1400 joules. After that, you solve for the math straight away. So it's like a 3 steps process. But if you look at it from a kinematics point of view, it can easily go up to at least 6 or maybe 9 steps in terms of math. So I'll leave it to you. Okay, if you are more inclined for math, you are good at math, okay, kinematics is actually a possible approach. Okay, if you're looking for a straightforward approach, okay, energy approach is actually short and sweet lah, in a sense. Okay, but as a student, as a physicist, okay, as a student learning physics, I would say that it's utmost important to actually understand that two approaches are actually workable, okay, in any situation, in this situation. Okay, so it's important for us to actually understand how we can approach a particular situation with a concept, and how this concept can actually be linked to the previous concept that we actually have learned. Okay, this is one classic example to show us that how physics are like intertwined or different concepts, but they actually go around in circles, coming back to with each other. Okay, so if you have time, okay, just look back at this recording to see how I actually uses conservation of energy to solve this question. And after that, I end off with using kinematics to solve this particular section. Okay, it is a nice twist to it, but it's good to know. Okay, and more importantly, is that it further validates us that all the concepts are related. Okay, with this, if you have any problem with conservation of energy, okay, look back to my previous video on energy. If I'm not wrong, it should be video 6.2. Okay, to look at the basic and the formulas for this particular topic. Okay, if not, the next video I'm looking for will be, if I'm not wrong, will be exercise 7.2. It's one interesting question. Okay, stay tuned. Bye bye.